Hi, everyone. Welcome to the online seminar on the mathematical foundations of data science. Thank you all for joining today. Our seminar is generously sponsored by 2 Sigma. It's my great pleasure to introduce our prestigious speaker, Professor Matthias Cattaneo. Professor Cattaneo is a professor of operations research and financial engineering at Princeton University, where he is also an associated faculty in the Department of Economics, the Center for Statistics and Machine Learning, and the program in Latin American Studies. His research spans econometrics, statistics, data science, and decision science, and has in particular made fundamental contributions to program evaluation and causal inference. Professor Cattaneo is currently an Amazon scholar, and he has advised several governmental, multilateral, nonprofit, and for-profit organizations around the world. He also serves in the editorial boards of the Journal of the American Statistical Association, Econometrica, Operations Research, the Journal of Business and Economic Statistics, Econometric Theory, the Econometrics Journal, and the Journal of Causal Inference. So today he is going to talk about Binscatter methods. So without further ado, please join me in welcoming him.
Okay, thank you so much for such a wonderful introduction. I'm not sure I deserve all those kind words, but nonetheless, I appreciate them very much. And thank you for having me today. So being this a data science seminar, but at the same time, hoping to touch on foundational aspects, mathematical foundations of that. So I chose this paper, which I hope kind of reflects a little bit of those 2 goals. So on the one hand, it's a paper that speaks directly to practice in data science, broadly defined, but at the same time has a couple of more technical contributions, which are mathematical in nature and are foundational in a very precise sense. And so today what I'll try to do is try to walk you through a little bit of those 2 aspects that are kind of merged together in this work. So the title of the paper is On Binscatter. On itself is a little bit provocative. When one puts on in front of something, it attributes a lot of presence to what comes next. So what I'll try to do today is also motivate a little bit of what Binscatter is and how it's used and interpreted among social sciences, behavioral sciences, and data science in more generally. So this is joint work with Richard Crump at the Federal Reserve Bank of New York, Max Farrell at University of Chicago, and Yinjie Feng, currently at Princeton, but not for long. He's joining Tsinghua University soon. What I'll do today is I only have 50 minutes, and I'll try to give you an overview of what this work is about and how it contributes to the different literature. So I'll do a quick introduction on what this problem is and why we decided to work on it and what kind of ideas and problems we faced as we started thinking about this. And then I'll give you an overview of the main results that we have. But then I'll try to spend a little bit of time, at least 20 minutes or so, on the more theoretical contributions that underlie this paper. So I can give you a little bit of a flavor of what are the more foundational mathematical foundations that we rely on, and hopefully some of the new things that we were able to provide more generally. Okay, great. So let me start by defining things. So Binscatter is a concept, it's an idea, it's a way of analyzing data, and it's quite popular in economics and many other disciplines. You find this type of procedures being used all over the place. Economics is perhaps the predominant one, but you also see it in marketing, in political science, in biostatistics, in many other areas. It's essentially a way of summarizing data that then researchers often use as a starting point to try to do other things. And so The one thing that I should mention at the outset is that you will see tons of connections as I start describing what Binscatter is and how researchers usually use it in practice. You'll see tons of connections with other literatures that you may or may not be more familiar with. So I try to present here 4 of those at least, which hopefully at least one of them will resonate with any one person attending this seminar. So you may have heard of the so-called regressogram, which goes back all the way to Tukey 1961. You may also have heard of subclassification as an idea that goes back to Crocan in 1968. And then if you come more from the finance side of things, you might have heard of ideas related to portfolio sorting, which was proposed originally by Fama in 1976. And then if you are more of the machine learning or even in the more recent data science stream, then you would have heard probably of regression trees. Which was originally proposed, I guess, by Friedman in 1977 in one way or another. And so all these methodologies will be closely related to what people usually call or refer to as Binscatter in social science, in behavioral sciences. And so you will see the connections, and then hopefully you could also imagine how some of the results we're going to present today could also be ported to these other literatures. And I'll make a few comments along the way when we get there. So what I'll try to do today is try to discuss more generically what Binscatter is. And then based on it, the paper basically has 3 main contributions. These contributions span what I usually regard as the 3 main goals that a paper has to have. It will have a methodological contribution that is trying to inform practice, trying to help practitioners to use these methods in a more appropriate way. So in the context of this paper, we're going to actually give some guidance in terms of what is valid. Some of the things that practitioners are currently using or doing turns out to be valid, but then also we're going to mention briefly some of the potential pitfalls or things that may not be valid, even though they rely on them or they use them regularly in practice. And so I'll get to that in a little bit. And then from the theory side of things, as I mentioned before, I'll try to spend the last 20 minutes of today's talk trying to discuss a little bit of how we address some of the more technically challenging problems in this paper. And so in particular, we had to develop what is generically known as a strong approximation. So we had to develop a new type of a strong approximation and then circumvent some technical issues in order to be able to do a uniform inference on certain procedures, as you will see in a little bit. And so that prompted us to obtain some new results along those lines, which I'll try to describe in some detail towards the end of today's talks. And then from the practical perspective, so one thing that I like to do a lot when I work on problems like this that try to merge together practice and theory, I always try to provide software that people can rely on and then hopefully use in their own research. And so if you're interested in testing some of the results that we have already available in software form, general purpose software, you can come to this website and check it out on your own. We're in the process of upgrading all these, so some of the results I'll present today are not in the paper as of now, but they will be soon in the next couple of weeks. We're in the process of revising the paper and the software packages. Okay, so what is Binscatter and why people tend to like it a lot in some areas or some areas of data science? Well, let me just explain it by showing you what it is. So I should say that there is no one thing called Binscatter. So if you go to the literature, you see different people doing this in different ways. So today here, I'm going to try to give you an stylized description of what I believe to be the simplest and the typical implementation of Binscatter, and then hopefully walk you through how this can be changed, expanded, generalized, and so on and so forth. So typically, researchers are confronted with data, usually large data sets. So here's one such example. And so these dots reflect individual observations relating some outcome of interest Y with some covariate X. Okay, so here for simplicity, we're thinking bivariate vector of random variables. And then what practitioners relying on Binscatter usually do is they take this data and then they form bins that split the support of the independent variable according to some rule. And so the typical rule in practice that researchers often use is some sort of quantile-based bins. So for example, here there are 10 bins, and so this the support is split along the percentiles of the distribution of the random variable x. So once you form those bins, then what the researchers typically do is they construct some measure of centrality within each bin. So in this example, I'm giving you the sample average. So each of these dots here represent one sample average using only the observations that fall on a given bin, right? So this is very much similar to things that you may have seen before. So in that sense, there is nothing new here. It's just trying to get you to what practitioners often do in practice. And so then once they have grabbed all this data, they have binned it, and they have produced these 10, in this example, 10 sample means, what researchers do is they basically remove the data and they report these 10 dots as what they call the Binscatter of the data. And then usually what they also do in practice is to superpose these with some parametric fit on the overall data. And the underlying idea of comparing these two is very much the idea of non-parametrics or smoothing techniques. So what they're trying to say is, well, look, we can look at the data and basically bin scatter along those bins, or we can try to fit something that is more global, perhaps a linear regression on the raw data, and then try to compare these two. So try to understand to what extent the parametrization of the condition expectation of y given x by, say, a linear regression is far off or not from these bins or these sample means that have been binned along the support of the variable x. And so just to give you an idea, this is an example of many that you will find in this type of empirical papers and journals. So in this particular, this is taken from the American Economic Review, which is a very important journal in economics and social sciences, and is by Rush, Jerry, Friedman, and Rockoff. And basically what they try to do is exactly what I described before. So in this example, they have 4 million observations. They decided to use 20 bins. And so here there are 20 of these blue dots, each of them corresponding to the sample average within one of the 20 bins that have been constructed by looking at 20 quantiles, evenly split quantiles. And then they actually overlap these with the linear regression on the raw data, the 4 million plus data points, and then they look at this graph, right? And so this is a way of summarizing the non-parametric feature of the data vis-a-vis some parametric approximation thereof. And then what they conclude from this, well, of course, you have to go and read the papers. Different papers do different things with this. But usually one thing that they typically like to see is that these dots are not that far off from the line. So they use this as a visual, perhaps informal check on whether the relationship of the outcome variable and the independent variable happens to respect this parametrization that they also decided to use. So in this case, linear. So is the relationship of y given x linear? Well, one way of asking that question is how far out are these dots, which represent the local behavior of the condition expectation relative to the line. Right? So that will be a very obvious question to ask. And in practice, often practitioners present this plot, they look at this graph and they quickly say, well, this looks fairly linear. So from now on, I'm going to move on and use the linear model to analyze the data. So it will be more of a specification test type of idea. Of course, there is no formal theory for this, but essentially they just rely on this visual inspection to try to assess the linearity of the relationship of y given x. Okay, great. So with this type of motivation, this is where we come in. We say, well, look, this is extremely popular. It has been used widely in empirical work. So would it be possible to formalize some of the procedures that practitioners used, and can we actually improve them? And so the goal of this paper basically will be to do exactly that. So what we're going to do is we're going to go back to the literature. We're going to see how practitioners often do this, and then try to encode everything that has been done in practice into a formal or a formal model or a framework to understand a Binscatter. And so we're going to do that in 3 stages. So first and foremost, we're going to try to be as respectful as possible about what practitioners really do. So if practitioners decide to use quantile space binning, i.e. constructing these bins based on the quantiles and estimated quantiles of the distribution of X, then we are going to enforce that. We're going to use that. And so that will bring some headaches, of course, as you will see in a minute. But I mean, technically speaking, can be handled with a little bit of extra work and more care. And we're going to do that in order to respect practice. If practitioners decide to include other covariates, then of course we're going to do that as well. We're going to try to think about how covariates should be included in order to mimic or at least improve practice in that regard. And then also we're going to do some extensions. So this is something that some practitioners do, but not many, where you could actually think of extensions of this basic procedure where you compare the dots to the lines by, for example, considering higher order polynomials within the bins, or perhaps smoothness constraints across the bins when you are forming those estimates. And so we're going to try to do that as part of the analysis. And then more importantly, so far I talked about reporting the sample average of within each bin of the outcome variable of interest, but many times you may care about other things. For example, you could care about the quantiles of the distribution of Y given X at those particular bins. And so of course, when you start thinking about that, you start thinking about more generalized ways of estimating relationships, features of the relationship of Y given X. And so we're going to generalize our methods to cover what I call here semi-linear quasi-MLE or maximum likelihood methods. And I'll define all this precisely in a few slides, but it will give you an idea of, okay, now we don't only care about the mean of the distribution, we may care about the quantiles of the distribution, or we may care about modeling the condition expectations in other ways, for example, logistics or Poisson regressions or things like that. And so once we have set up this general framework or generalized framework, then we're going to go on and do some theory. And so the purpose of this is, I mean, if you agree on the framework, then hopefully that gives us a common language. And now we can start answering questions that practitioners may care about. For example, how to choose those bins. Should you use 20 bins? Should you use 100 bins? Where should you place them? So these type of questions now we can answer because we have a formal framework. So we'll do something about that. And then we're going to start thinking about this problem from a non-parametric smoothing perspective in order to try to understand its properties. And so in particular, something that practitioners care about, although they don't often report, is the uncertainty around the estimates that they produce. So going back to this example, each of these dots are averages over quite a few number of observations, right? So roughly 4 million divided by 20. So about 200,000 observations in each bin, but still you would like to understand what is the uncertainty that each of those carry. And so, of course, in order to do that, we need to understand the properties, the statistical properties of the estimator that underlines the construction of these dots. And then, more importantly, we would like to form statistics, formal statistics that allow us to tell, okay, are these dots surprisingly away from the line, or are these dots just part of the natural uncertainty in the estimation, and they are no different than the line. And so in order to do that, we're going to need to develop some valid hypothesis testing for parametric specifications and also for shape restrictions. So we're going to provide some results along the lines of interpreting the relationship of these dots over the support of X. And so to do all this, actually, we're going to need to rely on some new theoretical results. And so in particular, we're going to use something that is called strong approximations or coupling techniques, which come very handy in this particular setup, as I'll discuss in a little bit. And that will give us the power to analyze a bunch of things all at once with the same technology. So we're going to be able to construct confidence bands when we view these dots as trying to approximate conditional expectations or other functions like that. And then on top of that, we're going to be able to develop valid hypothesis tests for a bunch of features that pertain to the underlying function itself, such as, is the function convex? Is the function increasing? Is the function linear? Is the function quadratic? Is the function constant? And so all these questions can be formalized once you have a good handle of this uncertainty that underlines the estimation of the function itself, which we're going to achieve using these coupling techniques. Okay, Very good. So let me quickly try to give you an idea of how we build this framework. And then once we have the framework in place, I'm going to skim over the results that are technically not challenging or not different than standard in the literature. And then I'm going to zoom in to these strong approximation results to try to give you a sense of how things work. But in order to do that, I need to walk you through the framework that we put together in order to analyze this problem. So I'll start by that. So here's an example of another data set. The gray dots are, again, the data itself. And then in this context in particular, we know, because we have generated this data using simulations, we know what the true conditional expectation of the outcome variable given the independent variable is. So in this context, the black line here happens to be the true conditional expectation. And it's purposely not linear everywhere, but it's linear in most places. So it's linear around here, but then there is this bump in the middle that happens to be non-linear. And so that will give us an interesting thing to look at, because we're going to start comparing the behavior of Binscatter methods vis-a-vis other methods to approximate this conditional expectation and how that performs. So how does Binscatter methods work in this case? Well, I already explained to you. You form these bins based on quantile-based knots. Or partitions. And then once you have that, you construct these sample averages. So sample averages are reported as dots, but in reality, sample averages are nothing more than constant regression. So effectively what we're doing is running locally to each bin the regression of y given x on x, and we're just estimating it by using a constant function. And so when you do that, then you get those dots there, and then you can actually compare them to, say, a linear regression on the whole data, just like I showed you before. So the question would be, in this case, these dots are fairly on top of the line, whatever that means. We're not being formal here, but visually they seem to be close to the line. And this here, they don't seem to be the case. Well, of course, we know that the underlying data generating process has a bump around this area. And so the question is, can this methodology formally tell us whether this is surprising enough to reject the linear specification? And so that's exactly where we're going with this, right? So we're trying to pin down whether these local approximations of this conditional expectation would be good enough to tell us, oh, in reality, this distance is large enough to reject the null hypothesis of having a linear specification of the conditional expectation. Okay, great. So as I said before, we're just fitting constant functions within each bin. So we now can formalize that idea. So here is a formalization of that basic idea. And this is what I'm going to refer to as the canonical Binscatter. It turns out that if you have some background in classical non-parametric smoothing, you will recognize these as nothing more than a series regression where the series basis is a hard basis. So essentially what you're doing here is forming bins, and then for each bin, you're running a constant function within each bin. So how do we formalize this idea? Well, the outcome variable is y, there is some unknown function mu of x, and there is some residual epsilon I. And then the estimators, this Binscatter function, if you view it as a function, trying to estimate the conditional expectation of y given x, is nothing more than the regression of y on a particular basis construction. And that particular basis construction crucially has a hat on it. So that will bring some issues to us, and I'll discuss them along the way. It has a hat there because, as I told you before, those are nothing more than constant functions, but they are constructed on estimated bins. So the knots had been estimated, and in particular, they had been estimated by looking at the quantiles of the x variable. So in other words, you first find the j quantiles, evenly spaced quantiles on the support of x, that forms the knots, and then that forms these j indicators. And then once you have those j indicator variables or indicator functions, then you can run the regression of y on that basis, and that will give you immediately j sample means. So here we are estimating j parameters, and those parameters are the j sample means, which are the j dots in the Binscatter. And so this is the graphical representation of that very simple idea, which is what people do in practice. Okay, of course, once you do constant fits, naturally you can ask the question, why not linear, why not quadratic? And that's very easy to encode. So once you start putting more into the model, it's very easy to enlarge it. So in this example, for example, if you wanted to go from constant to linear or quadratic, all you really have to do is to enlarge the basis within each bean that you decide to use. So instead of using a constant basis within each bean, now you can use a linear basis or perhaps a quadratic basis or any order that you like. And so here P will track that. It will track what is the polynomial order that you are using within each base, within each bean. And this has an important advantage. The moment that you decide to use more than a constant function within each bean, now you can ask questions about, for example, derivatives of the function. So because we have a P here larger than 0, then we can ask questions about what is the derivative of the function or the change of the function locally to that P. Right? So intuitively, if you run a linear regression within each bean and you look at the slope, that will give you an idea of how the function is changing along the support of X. And so this basically is very easy to do. You just dump these polynomials inside, and then immediately you get a more general Binscatter approach. Okay, great. And so then, of course, once we go from constant to linear, and from linear, we can also do connected, obviously, right? So this is very easy and very simple. I'm going fast for that reason. Essentially, the idea is, well, once you decide, okay, constant is not good enough for me, I may do linear or quadratic, then naturally the question is, if you're going to expand the basis within the beans, why not also restrict the fit across the beans? And so, if you're familiar with non-parametric smoothing, you will recognize that this idea is what we call splines, right? So splines takes these local supported polynomial bases, and then they're connected along the beams. And that's exactly what we're doing here. Just we're embedding this technology into something that is well known in the literature. And so how do you do that? Well, it's not very difficult. So again, you try to estimate the conditional expectation of y given x. And now what you're doing is kind of enlarging the basis a little bit more, or in this case, constraining the basis, actually. So what we're going to do is still run the regression of y on the basis P. But now, importantly, not only we allow for polynomials, of course, in order to be able to be flexible within the beans, but also we would like to be constrained across the beans. And so it turns out that you can find linear constraints that ensure that you are, for example, twice continuously differentiable if you decide to use a cubic polynomial within each bean. So you can actually ensure that at the nodes, you are twice continuously differentiable and therefore everywhere. Okay, so this basis is well known. It's not unique, of course, but here we're going to choose the B-spline representation. And then the only trick or the only difference that, again, make us pause for a minute is that there is a hat there. So by a hat, what I mean is that we need to estimate something to begin with. In this case, the position of the nodes, which we estimate looking at the quantiles. And then after we estimate the nodes, then we form this basis of this matrix of constraints to ensure that the smoothness is imposed across the beams. Okay. Very good. And so then the next part in the construction of the framework, in order to start talking about theory, would be how we actually do covariate adjustment. And so in this paper, what we consider is a semi-linear approach. So we're going to consider estimating this function mu, or perhaps the function mu plus the covariates, but then the covariates will enter linearly, additive separately. So in this context, we're going to think about a semi-linear function where we are now fitting our basis, spline basis there, and also some additional covariates that enter additive separately here. Okay, and so that will give us two estimates, beta hat and gamma hat. And then if you just care about the mu part of the conditional expectation of y given x and w now, then quickly you realize that all you need to do is to still look at the basis prime, the least square coefficients on beta here. Okay, very good. So far so good, nothing crazy at this point. I should mention, however, that in practice, many times researchers don't do this. Researchers, what they do is they instead use an idea related to residualization. which is a little bit different from what we are proposing here, and actually is not always delivering the correct estimates. So just to give you a 2-second summary of what they do sometimes, they take this additional covariates W, and then they regress out the covariates using a linear specification. So they basically regress from X the covariates W, and then produce some residuals, and then they regress from Y the covariates W and produce some residuals, and then grab those residuals and use them as the basis for constructing a Binscatter. So as you can see, this will not agree in general with this method up here. And the reason is pretty clear, because as you well know, residualization works only when you have a linear model. If the model is nonlinear, residualizing first and then doing non-parametric estimation will be different than running the partially linear or semi-linear regression model. So there are some issues related to this, but for the interest of today's talk, I'm going to skip on them, and I'm just move on to some of the more interesting theoretical results that we have. So if you are with me with all this framework, now you realize that the model that we're thinking of is an outcome variable Y and some partially linear or semi-linear structure on X and W. And then we're estimating it by using some basis that is kind of these splines with estimated knots, and then some additional covariates that we adjust for. Good. So now what is the next step? Well, let's think about uncertainty estimation or quantification. So the natural first question would be, how can we form confidence intervals for this function at some point, or perhaps how we could form confidence bands for some function, for this function as a whole. And so here is a typical formula that you, I'm sure, are familiar with. So a natural way of constructing confidence intervals or confidence bands would be to take the point estimator at each point, at each evaluation point, little x, and then choose an appropriate quantile, and of course, studentize by an appropriate standard error formula. And so the key of the matter here is which quantile to use in order to form these intervals. Well, if you're interested in confidence intervals, then you choose the usual, I'll mention this in a minute, you choose the usual Gaussian approximation for the studentized T statistic, and then immediately you get a valid, point-wise valid confidence interval in large samples. And so that's exactly what we're going to do in this paper with a couple of extra wrinkles. But then more interesting of a question would be, how do you form a confidence band for this function estimate? And so there is a little bit trickier, because now you don't want to assess the uncertainty of your estimate at any one point on the support of the variable x, but ideally you would like to understand the uncertainty uniformly over the entire support of the variable x. And that turns out to be quite more challenging, and there are different methodologies to do so. And here in this paper, we propose a different one, and one that actually has some demonstrable theoretical advantages that I'll mention when we get there. But intuitively, what we're going to do is basically grab our T statistic, view it as a process indexed by the support of the variable x. And then what we're going to do is we're going to construct a couple to that process that is close and constructed in a very special way and is close to it. And it happens to be a Gaussian process. And then what we're going to do is basically show that these two are sufficiently close that we can pretend that the distributional features of the original T statistic process can be well approximated by this coupling Gaussian process. And so we're going to do a flip. And so this notation here, which means nothing to you at the moment, will actually be this particular Gaussian process. So I'll walk you through the construction in a few minutes, but basically I'll show you that at the end, what we're going to be doing is essentially constructing a Gaussian process that is close enough to the original T statistic process that we can do the flip, and then use that Gaussian process as building block to construct confidence bands. And so I'll walk you exactly through those ideas in a minute, but intuitively will be nothing more than simulation from a very particular statistic, the suprema of a Gaussian process. Okay, good. So here's a picture of how these things will look like. So these are the confidence intervals that you can get at different evaluation points. And then, of course, the confidence bands will be larger because they are covering the entire function with preset probability. Okay, awesome. So then what about specification and shape restriction testing? Well, once we understand how to handle the uncertainty of the function estimator as a function or as a process, now we can start asking questions such as, is the function constant, linear, quadratic? Is the function positive or increasing or perhaps convex? Or we can even ask questions about other type of things like that. And so all these things are going to be formalized in a couple of minutes, but it will all rely on the same strategy based on this strong approximation result that I'll describe in a few minutes. And so I think, in a sense, this is the most useful part of the paper because it will give researchers the opportunity to formalize ideas such as, oh, the dots are close to the line. Can I just conclude that the condition expectation of y given x is linear? Or things like that. Okay. Great. So here's a graphical example of what I just said. Imagine that you have a bunch of these dots and you have these confidence bands, which are purposely not very smooth out at the moment. And then you would like to compare those non-parametric approximations with perhaps a constant fit, like this one here, or perhaps a linear fit to the data like that, or perhaps a quadratic fit to the data like that. And so are these statistically indistinguishable? And so, of course, it depends on the statistic that you decide to use, but naturally you can see that these fits are very much in some areas outside the confidence bands. And so those functions don't land on the confidence bands. And so naturally you would ask the question, is that enough evidence to conclude that we should reject the null hypothesis of the condition expectation being linear, quadratic, and so on. And so I'll show you a little bit of those ideas in a minute. Okay, great. And then finally, the last thing that we do in this paper is kind of upgrade everything that I just told you from least squares regressions to quasi-MLE. And so here, what the type of model that we are after is a model where we're going to have a link function that is called eta, that is going to be assumed to be a smooth. And then we're going to have another loss function called rho, which we're not going to assume is a smooth. It's going to be piecewise Lipschitz, so we can account or accommodate quantile regression as well. And so at the end of the day, what we're going to do is basically upgrade all the results, including the strong approximation results, to this type of estimator, which is a quasi-MLE type estimator. And so this will cover, for example, the Binscatter that we discussed before, if you use quadratic loss function and identity link function, but it will also allow, for example, for generalized linear models like Probit, Logit, Poisson regression, and so on, if you use a quadratic loss, a nonlinear least squares type of setting, and then you use some non-identity link. And more importantly, if you change the loss, for example, to the check function, then you can also think about quantile regression. So we can think about what is the conditional median regression of y given x and w, and then we can all of a sudden use the same ideas in the context of Binscatter. And so the interesting thing here is that, of course, once you upgrade to this type of setup or estimator, then the analog estimands lead to interesting parameters. So now the parameters of interest have been enlarged by quite a bit. And so here there are a couple of examples of other parameters that you may care about. So this is a parameter that is sometimes called as the partial effect, because you just look at the average change or the marginal change at a point x on y, looking at the particular link function in that model. Okay, and so we're going to be able to analyze all these parameters using the theory that we develop in this paper. Okay, great. So in the last 15 minutes or so, I'm going to walk you through the main theoretical results. I mean, we have quite a few in the paper. I'm just going to zoom into one of them, which is this idea of a strong approximation. So I'm going to try to walk you through how we do that. And so then with that, hopefully the rest is going to, you can always just go and read the paper. So just to get you back to the setup, for now, I'm going to focus on the special case of identity link function and quadratic loss. So we're back to partially semi-linear least squares regressions, if you like. But later I'll show you how this extends to the other cases. And so once you have this defined, and hopefully you have been following me. We also have the random beans generated by the quantiles in the data. Now we are ready in business to start thinking about what we can learn in this context. So one thing that we do in the paper quickly, just to mention, is that we establish a valid integrated mean square error expansion that allow us to ask questions such as, what would be the optimal number of beans that you should use in this context? And so it turns out that there is a formula for it that now we can provide to practitioners to just naturally decide how many beans should be used relative to the sample size that they have, as well as other features of the model, such as the local variance or the integrated variance and the integrated bias. This is not particularly surprising or novel at this point, but we just have it there as a starting point to try to organize our thoughts. Okay, great. And so then as a building block to get to the strong approximation results, let me quickly mention the idea of confidence intervals. Again, this is pretty straightforward from the literature. By now, there are several papers that have established this in different ways and forms, but usually they all start the same way, and it allows me to introduce basic notation that I'm going to use in the next couple of slides. So think of the standard t-test statistic. At this point, think of it point-wise for the evaluation point X. And then we have the non-parametric estimator centered and scaled by the square root of the standard error, by the standard error of the estimator, right? And so here, remember, as I showed you before, and hopefully you believe me, at least when the loss function is a square loss function and we have the identity link function, this boils down to least squares regressions. As a consequence, the formula of gamma hat is pretty straightforward, right? Of the usual sandwich form. So you're going to have the Gram matrix inverse on either side, and then you're going to have in the middle the variance of the score, if you like, in the context of least squares regressions. And that one here will look exactly like this. So this is nothing more than just the residuals, right? In the least squares regression. And then this is nothing more than the basis that you're regressing against. Okay, so it's pretty straightforward to show that point-wise in this little x, a central limit theorem holds. And this statistic converges to a normal random variable. So that immediately gives you a natural way of forming valid, asymptotically valid confidence intervals. So you just go and grab your preferred quantile from the normal distribution, let's say 1.96. And then you literally grab your point estimator and you bump it up and down by 2.96 times the standard error. And that gives you the usual confidence intervals that are valid point-wise at each point on the support of X. So now these guys look like that, right? So pretty straightforward, nothing fundamentally new there. But now the question is, what happens if we want to do more? What happens if we would like to view this statistic not as point-wise in X, but rather as a process itself? And so when we start thinking about it, we start thinking about it as a stochastic process, which is actually a t-statistic process that is indexed on the support of X. That is nothing more than the one that I just showed you before. And here is where things get a little bit tricky, because I mean, in this type of settings, this process doesn't converge in distribution to anything. So basically, what happens is that this process starts becoming more and more independent at different and nearby points, and eventually it starts oscillating too much. And so it never settles down, and it's not possible to characterize its limiting distribution. And so at that point, you are kind of in a little bit of a difficult position, because it would be hard to develop distribution theory for many statistics of interest that are functionals of this process if you are not able to establish a distribution approximation for the process itself. And so among those statistics, natural ones would be, for example, the suprema of the process, or perhaps the infima of the process. And so these are going to be statistics that are going to pop up in a couple of slides, and though all of them are functionals of the process itself. So if we wanted to get an understanding of the fluctuations of the process, an approximation to that, to the distribution of the process, then we will need to do something else. And so what we do in this paper is basically to use a couple of tricks. And the most important one builds on an idea, which is the idea of the Hungarian construction to do a coupling. So what is intuition here? Well, the intuition is very, very simple. You have a sequence of random quantities, in this case, stochastic processes. They don't settle to anything, so they don't converge in distribution to anything. But nonetheless, we can form another sequence of random quantities, in this case, stochastic processes, that would actually get closer and closer and closer to the process that we are interested in the first place. And so that's the idea of coupling, right? So we're going to try to find a second process that hopefully we have a good handle on, for which the two processes are close in a very precise sense. And so even though the original process is not settling to anything, this other process is going to start doing a very good job at keeping track of the original process. And so there we can do the flip. We can essentially rely on this other process as an approximation to the original process in distribution, so that we can actually use the second process, the one that we constructed, to approximate quantiles of the underlying finite sample distribution of the original process. And so here's the one-line summary of this idea, and then I'll show you how the construction is done in this paper. So the way we do this is we basically start with the original T statistic process, and then we find a new stochastic process, which I call Z sub P. And this new stochastic process looks very much like something that you would have expected to see, right? So if you look at this statistic process is very much like the least squares regression of y given x, centered, and then standardized or studentized by standard errors. And so here what we do is essentially we do that. So we grab the new process, and we take all the pieces of the least squares kind of numerator, if you like, and then the denominator is actually exactly kind of that, if you see, very close to that. But then crucially, we do one replacement. The replacement that we do is that we replace this last piece of the stochastic process by a vector of normal independent random variables. So intuitively what we're doing here is we're effectively expanding the original process, and then we are replacing the residuals in the center and scale original process by normal random variables. And so that's where the coupling technique comes in. And then we rely on that to actually construct the stochastic process that approximates well the original T process that we started with. And so up here, approximate well, it has to be defined. It's in a very precise sense. So for the purpose of today's talks, I'm just gonna give a quick definition. It's just gonna be being closed in a uniform norm in probability at a certain rate. Right? And so, of course, this rate here will matter a lot, but it's going to be a rate that goes to zero sufficiently fast that allow us to claim that the original process and this new process are getting together uniformly on a same and large probability space. Okay, very good. So how do we do that? So let me try to give you the four-line intuition of how we actually do this. So remember, the goal is to try to show that the original process here is close to this very last step down there. So we're going to decompose this in a couple of steps. So the first step is going to be very simple. We're going to grab the original process, which has a bunch of estimated quantities, and we're going to show that you can construct another process that it looks very much like the same process that you started with, but it took all the hats off. And so here we take the hat off of the matrix of smoothness constraints across bins. We take the hat off of the gram matrix of the regression portion. We even take the hat off inside the basis that approximates the regressions, the bins, right? That has these estimated quantiles. And then this error here is nothing more than the residual of the underlying model of y given x. It's conditionally means zero, of course. Okay, great. And so the only thing that we didn't take a hat off, crucially, is from this portion here. And this turns out to bring quite a lot of problems because without getting into the technical aspects of this, we are effectively plugging in an estimator, a quantile of the distribution of x inside an indicator function. So these bases here, think of them as being indicators. In the simplest possible case, those are indicator functions that partition the support on some estimated quantiles. And so no matter how fast or how well those estimated quantiles approximate the true quantiles of the distribution, the indicators are sufficiently discontinuous that from a uniform perspective, it will not be easy to get rid of that extra noise or that extra error in estimating the quantiles. And so, unfortunately, for our purposes, at this stage at least, we need to leave those in. We cannot do anything about that because the Suprema here forces us to not be able to remove that randomness from the process. Nonetheless, we can still define this stochastic process indexed by the evaluation point little x, which enters in particular that basis, a hard basis, and then we can form this intermediate stochastic process. Great. So then what do we do next? Well, then we develop a new conditional coupling, which is based on the idea of the Hungarian construction. So if you are familiar with this idea, it's a way of constructing a new process that lives on a large probability space that preserves certain properties relative to the original process. But crucially, one thing that we do is it allows us to change the original residuals underlying the data generating process by now normal random variables that preserve the same covariance structure. So in other words, we go from, let's say, a mean zero bounded conditional variance residual arbitrary distribution to one that now is essentially mean zero conditional variance the same, but is Gaussian. So we have restricted the rest of the shape of the distribution of the underlying residuals. And so this step here is crucial, and that's where there is some non-trivial work to be done. And then the final step is essentially to go from this conditional coupling approximation to an unconditional coupling approximation. And so there we again show that you can actually grab this statistic and basically approximate it by another stochastic process that now has been essentially, the randomness that this portion of the statistic has been all summarized in a non-random quantity, which is this conditional or this unconditional variance, plus a vector of normal random variables. And so when you look at this expression here now is exactly what shows up right here, right? So we basically went from something that contains all the randomness of the original statistics to something that is basically controlled by these normal random variables. Okay, cool. And so then from there, it's not very difficult to actually get approximations for different statistics, including, for example, the Suprema of the stochastic process. And so that's the kind of things that we do. Okay, great. So once we have those results, then it's not very difficult to realize that you can form confidence bands by just simulating from this Gaussian process, this approximating Gaussian process that is right there. So you basically sample from the normal distribution, you discretize, and then you basically compute the Suprema of that. And then that will give you an estimator of the corresponding quantile to get the confidence bands to work. Okay, great. And so those confidence bands look exactly like that. Okay, excellent. And so then quickly in a couple of minutes, how do we actually do specification testing or other type of shape restriction testing? Well, it's actually very similar. So what we're going to do now is we're going to look at another T process. The T process is going to compare the non-parametric fit to some parametric specification, let's say a linear regression, like I showed you before. And then we're going to ask the question, what is the probability of the difference between the two be zero in the supremum norm? And so obviously, in order to do that, we're going to need to understand what is the distribution of the supremum of the difference between the non-parametric estimator and the parametric estimator. But that is very much similar to what I did before. It's trying to understand the law of the supremum of this particular stochastic process. And the same type of theory that I showed you before can be applied in this context as well. And you can actually capture quantiles that approximate these the distribution by using this approximating Gaussian process and then computing the suprema of that on a simulated grid. Okay, great. And then similarly, we can test things like, is a function constant or is a function increasing or other things like that, which again can be done directly by looking at the supremum of statistics like this. And then again, you can actually approximate the quantiles by looking at this as a process, approximated by this Gaussian process that I showed you before. And then that will be used here to try to approximate the quantiles of that distribution. Okay, great. And so here's an example of how you can do that now. So this is a table that shows how we do it in practice. So these statistics here are nothing more than those things that I showed you before. And you can test for whether the function is constant, linear, quadratic, whether it's negative, increasing, concave. These are all features of the function itself that you can do once you understand what the suprema of those particular features of the function are. Okay, great. Excellent. And so in my last 3 minutes, let me just mention quickly how do we extend all these to the more generalized case where you don't have an identity link function and you may not even have a differentiable loss function. And so, and also in the process allow us to cover other parameters or estimators of interest. So what we do in the paper as well is to establish a uniformly valid Bahaur representation that essentially shows that even though the estimator now is fundamentally non-linear, perhaps based on a loss function that is not even differentiable everywhere, then you can still nonetheless show that after centering, it is sufficiently close in a uniform sense to what it looks like effectively like the original linearized least squares type estimator. And the difference comes from a penalty, which is the standard penalty if you have done work before in quantile regression settings or other settings like that, where you need to pay a little bit of a penalty in approximating this estimator by this stochastic linear representation of sorts that you have right here. And so the only change is that before in here, we had directly the residual epsilon I, and that was given in closed form. Now we are doing only an approximation. And so, of course, that involves more quantities that you need to control. And so at the end of the day, you can see that if you believe that we can get to this point, then from this point on, all the theory I showed you before naturally can be extended to cover this case. So the bulk of the work is in establishing this uniform Bahadur representation. As it turns out, in our paper, we are able to improve on previous results by quite a bit and get much sharper Bahadur type representations that allow us to deploy the theory that we want to deploy in this context. Okay, great. And so given I have only 1 minute, let me just finish off with some final remarks, and then I'll give you a summary of where you can find more about what I talked today. So Binscatter is widely used across disciplines. As I said before, the methodological and formal results that one would like to have to properly use it is somehow somewhat lagging relative to its popularity, I believe. And so in this paper, what we do is we offer a formal framework. We talk about how to choose the bins, how to form confidence intervals and confidence bands, how to do hypothesis testing for shape restrictions or specification, parametric specification. And we even discuss how to analyze other problems, such as quantile, nonlinear least squares, and so on, all from the lens of quasi-maximum likelihood methods. Okay, and perhaps the most interesting theoretical portion of this is that we are able to offer some new strong approximation results for a QMLE partitioning-based estimation. So if you're interested in reading more about this, here are the 2 papers that this talk is based on. So the first paper is co-authored with Max and Inge. It came out in the Annals of Statistics last June. And there, what we do is one of the main contributions of that paper is to establish this new strong approximation I briefly described today for the case of least squares estimators, partitioning-based least squares estimators with non-random partitions. So it's kind of the first step. And what I presented today is an important and non-trivial generalization of this or extension of this, where we now have these strong approximations for generic QMLE estimation. based on partition-based estimators for semi-linear series with random partitions. So essentially, we had to handle 3 more things in order to be able to make it to work for Binscatter more generically. And so that's what this paper does. And so the version that is currently in archives is a little bit dated. So we're writing the new version with a bunch of new results. So hopefully in the next month, you will be able to see the newest version on this paper. Okay, great. And with that, I should stop just to make sure that we don't run over.
Thank you, Matthias, for the great talk. So as for questions, the first question is as follows. So is it possible to allow the data to have some dependent structure, say X and Y follow a martingale process, or has a martingale error, martingale difference error?
Yes, that's a great question. So not in this paper. So this it's a fantastic question. So in this paper, we focus on IID data. I think in most of the context of Binscatter, data tends to be IID, but nonetheless, I completely agree with you. So one could think of time series structures where either this residual and or the covariates themselves could exhibit some time dependence. For example, a martingale structure or something else. So that is a great question. So it depends on what you mean, but can this be applied to that? So the short answer is yes, it can be applied to those settings. Obviously, there will be a couple of changes. Some will be, conceptually obvious, and some will be less conceptually obvious. So let me mention in the context of, I think, in the context of the inference portion of this, because that's where I think it's going to be most obvious. So the first one is here. Obviously, as you can imagine, this middle matrix here will change quite a bit if you have time series dependence, right? Because obviously you will have to take into account lags and leads in order to account for the time series structure. But that's okay. We know how to do that. We use some sort of heteroscedastic autocorrelation consistent type estimator, and we can stick it in for the standard error formula. This type of point-wise results will go through so long as you have the appropriate central limit theorems, either for martingale differences or for some beta mixing or whatnot. What is perhaps more interesting is, can you get this type of strong approximations for processes like this if you have a time series structure? And it turns out that you can. So naturally, you would not be able to get them with the same level of accuracy. So many times what happens is that these rates here are not as sharp as you would get from the IID case. Sometimes, obviously, they will depend on some measure of dependence in the data, right? So if you had a beta mixing type structure, then it will depend on how these beta coefficients decay and how summable they are, and so on and so forth. But certainly, strong approximations for time series data had been developed. They are not widely developed, but there had been some. And we are in the process of developing some of those ourselves for some other project. But certainly it can be done. Yes, it will be a different technique, but you can still get this type of strong approximations in those contexts. Yes.
Mm-hmm. Thank you. And the next question is from Che Guan. The question is how this approach handles data with heavy tails and estimates robust estimators to avoid the impact of outliers.
That's a great question. So part of why we wanted to encompass QMLE type approaches is because we would like to use things like Hoover loss function. So that will be something that our results currently would allow you to do. So if you are willing to use that particular loss function, for example, then you could, I'm trying to find it. Give me 1 second. Oh, here we go. Perfect. So here, for instance, you could actually use for raw function, you could use the Hoover loss function. And so that will immediately downplay the extreme values of the distribution of the residuals, and therefore lower, downweight those outliers in the data. Now, what you are more interested is in the moment assumptions on the residuals themselves, then the question would be, are these strong approximations valid when you only have a certain number of moments, bounded moments on the residuals, right? So for example, if you were to say something like this, and then you say it's bounded, right? So the natural question would be, what is this has to be? So the best results I know of, and some of which we have as well, require these to be greater than 2. But it doesn't require to be any more than 2 plus epsilon. So if you have 2 moments plus a little bit more bounded, then you are in business. With less than that, I mean, naturally, this type of Gaussian approximations may not even hold because the limiting process may not be Gaussian, right? So it may be something else. So at that point, all this technology kind of goes out of the window because, well, obviously you will have to rely on other type of strong approximations to different type of processes altogether.
Thank you. And the next question is from Tongzhou. The question is, for the testing, is it possible that the proposed test accepts both linearity and quadratic forms?
Okay, so just to be very clear, in the current context, what we provide, so maybe I should probably put it here. Well, let me see what the test is now. So the type of test that we are thinking of is a test that would answer one of those questions at a time. So first you will test the null hypothesis of, is the function linear? And then you could reject or not reject, right? So if we don't reject, we don't know. It's just like we cannot reject linearity. And then if we were to do quadratic, same thing. We run a quadratic regression, predict values, compare those relative to the local fit of Binscatter, and then we can reject or not reject, right? So, I'm not sure how to answer the part of accept. I'm not sure I would say we accept. We don't reject. And yes, it could happen that you don't reject neither linearity nor quadratic structure, of course. Yes, that will be certainly a possibility. Yes. Mm-hmm. So if you want to see it in action, I kind of did it super quick here, but as you can see, if you remember in this model, there was a bump, and the bump is what we are trying to pick up here. So the linear fit and the quadratic fit both seem to reject or should reject that specification because there is this bump. And indeed, if you look at the full support of the data, which in this case is 1,000 observations, the linear one, the p-value is 0.000, 0.002. So we're both rejecting the null hypothesis of linear and quadratic. So we're rejecting one at a time, but we're rejecting both of them. But now, interestingly, if you just look at the half support of the data, so in other words, if you were to split this data and rerun the procedure only on this half, now all of a sudden the function would look like this. So it may still not look very linear, but certainly quadratic may start looking a little bit more. And so we were curious to see what happens in that case. And indeed, here we see that now for the half support, the linear is barely rejected, and certainly the quadratic is not rejected anymore because effectively kind of looks quadratic in some sense. And you can see that in the graph, right? So this will be what happens if you only chop half of the data, and then you go and actually look at the data and rerun the whole procedure. Now the confidence bands basically show you this, and the linear and the quadratic are both very much inside. So it's harder to reject that. Okay. Very good. So I'll stop there. Yeah.
Yes. Thank you. And another question is about the dimensionality. So, how large the dimensionality of X can be in practice?
Oh, that is fantastic. So, I didn't want to get into those details because I thought for this talk it would be perhaps too technical, but certainly it's a great question. So, what is the main contribution that we propose in these 2 papers I mentioned, the one in the Annals and this one that we're working on now? Well, it has to do with the dimensionality, but the dimensionality here has to be taken with very much care. So let me try to find the right slide here to discuss this. So if you remember, there are 2 types of dimensionality. So one dimensionality is one dimensionality is a dimension of the covariate X. Another dimensionality is the dimensionality of the basis that we construct out of the covariate X, right? So I think in this paper it's called J, right? So if you decide to use J beams, then you expanded a univariate covariate into a J dimensional covariate space, because now you have these J indicators. And so what in this literature is interesting, both are interesting. So one is what is the dimensionality of X, the other one is what is the dimensionality of the basis. But typically in this literature, even if X is scalar, that still begs the question, how much expansions can we do on the basis before breaking the results? And so that's what we basically did in this paper. So in this paper here, up before our paper, what people basically were able to show was that J squared over N had to go to 0, or sometimes even J cubed over N had to go to 0 in order for up to log n terms, so for even the strong approximation to be valid. And so for a long time, it was believed that it was not possible to achieve strong approximation results where the dimensionality of the basis could be of order n, or slightly, basically slightly lower n. So what we showed in this paper actually is that all you need is this. So in answering your question, it's now known, in this paper we show that all you need is that J over N has to go to 0. And why is this a natural lower bound on how large J can grow without regularization, of course? Well, because J over N is the order of the point-wise variance, right? So if you think about it, if you run the regression of Y on X, and X is a dimension J, then for the point-wise variance to even be consistent, you're going to need to have J over N going to 0. And so this is a natural lower bound on how large, or an upper bound on how large J can be before breaking the least squares procedure altogether. And so up to this point, people believed that even that bound, nobody knew how to achieve it. And so then in this paper here, because we do this new strong approximation coupling type result, we're able to achieve J over N going to 0. So in answering your question, the largest you can allow for is J over N going to 0 up to log n terms. As for X, this result I'm mentioning here actually holds for X univariate. And then we have a generalization for X multivariate, where of course now this will look something like this. It will have like a D there, right? And this will have a D there and a D there, right? Because the restriction now will be relative to the dimension of the original X, which then is expanded through the basis. And then this result we can show in some cases as well, while in other cases we are not able to get all the way to J over N, but we're getting close to it. And so I encourage you to look at this paper if you want to see more of that discussion. We have a couple of long paragraphs and a remark explaining how this compares to the literature.
Great. So thank you. And maybe the last question. So it seems as during the talk you mentioned in the hypothesis test you can incorporate the shape constraint of the mu function.
Yes.
And so I was wondering, in terms of estimation or hypothesis testing or doing statistical inference, is it possible to incorporate a certain prior information about either X or the regression function mu? Say you mentioned this shape constraint, but what if the X, the covariate has some prior information, say it lies in some manifold, say a sphere?
Yeah, that's a great question. I mean, my first reaction would be, I don't know, so I haven't thought about it. The type of results that we have at the moment, we can impose constraints on the basis, right? Because again, there's a difference between the original X's and the basis, right? That we're using to expand things. So on the basis themselves, we can impose a smoothness constraints, no problem. But I mean, I guess your question also applies. What happens if you wanted to impose also monotonicity constraints? you may want to do that too, right? So we haven't done that. So the trick is because for the type of constraints related to smoothness, I think the graph made it clear, right? So if you come here, when I go to linear and then I go to smoothness type constraints, like continuity in this case, right? So I say, look, we're going to fit linear regressions, but we're going to ensure that the outcome comes back continuous. So that basically reduces the degrees of freedom, right? Because think about it, in each cell, you have two parameters, the intercept and the slope. So you will have a total of, in this set here, there you have a total of 2j degrees of freedom, right? For each beans, you choose the intercept and the slope. But when you come here, you are no longer 2j degrees of freedom because, I mean, let's do it intuitively. In the first bean, you choose the intercept and the slope. But then in the second bean, you're no longer free to choose the intercept and the slope because whatever intercept you decide to use, it has to fit the value of the function here, right? In order to make it continuous. And so we are decreasing the degrees of freedom by imposing constraints. And those constraints can be imposed by looking at linear constraints. And so that's why this here, here we write the dimension, right? So the dimension reduces the degrees of freedom because basically it reduces the number of parameters. So we're no longer estimating 2j parameters, we're actually estimating less number of parameters because some of those had been constrained, right? So you lose degrees of freedom. And so that is represented by a linear constraint. So that's easy to incorporate. If you now want to incorporate monotonicity or things like that, those are typically not linear constraints. And so that's where things get a little bit trickier. I still believe we can do it because our strong approximations will still go through, but then again, we will have to attend to the space that is constraining the parameter space, right? So it will be like a cone. And so we have to be careful about how to do that. And so we don't do that in this paper. We have done something like that in another paper, but not here. Yeah.
Thank you. Thank you so much. And it seems that's all the questions I have. And thank you again for your great talk, and thank you for your time. And also, we would like to thank all the audience for coming today, and look forward to seeing you next week. Thank you, Matthias.
Of course. Thank you so much for having me, okay? It was nice seeing you guys. Bye-bye.
Thank you. Bye.